say. Thank you. Thank you. Thank you very much all for your presence here. So I'm here to talk about ray tracing-based scientific visualization. This is a new thing that is really exciting in our field. I've been doing scientific visualization for, oh gosh, already 25 years, and I've seen a lot of changes in technology, in software and hardware availability. So let's see how ray tracing is changing our world today. Why ray tracing? This is what we're going to talk about. I will describe very quickly what is ray tracing and how it can enhance our visualization experience. We will go through two showcases. I have two videos prepared for you. One of them in fluid dynamics, where we will demonstrate volume rendering, which is an application of ray casting through high spatial resolution domains. And then we will see a visualization of a water-air interface in a jet that is a purely path tracing application. And then we'll answer the question, are we done with ray tracing? You'll see why. A couple of words about CSCS. CSCS is the home of Pitt's Date. Perhaps you've heard of the name of this machine, number 6 in the world in the top 500 ranking as of June 2019. Well, Pitt's Dane is a big cray machine. It also happens to be my visualization cluster. So I've got over 5,000 GPUs available to do visualization. Pretty lucky guy, you'd say. Faster computers, bigger data, and more complex data, actually. And that's the problem. Of course, we need, and we don't always need to show all the data. Give me 10 billion grid points. I don't need to see all those 10 billion grid points. I just need to see the interesting ones. So I need feature extraction, of course. But mostly I need enhanced perception. I need a better way to do my computer graphics job. In the past, we've used many tricks, for example, doing those fake shadows, actually, because those are fake shadows because this was done 10 years ago. But a picture I like to see because it really shows how we can enhance the depth perception through the use of shadows. Another example I used from molecular science here, where I'm dedicated to looking at a particular instant in this chemical reaction where one particular molecule is of interest, so I blur out all the rest. I don't want the scientist to be distracted by the surrounding. I want to focus on just one particular thing. Here's an example from a biomedical application where we run. Well, we have a CT scan of a bone, and then on the computer we put screws through that bone, and then we measure the stress. Now, there was something wrong with the simulation, and we could not figure out what the problem was. If you look very carefully here, if you follow my mouse, perhaps I will get to it right here. There's a crack, which is really not part of the simulation. So all those things, looking at something very tiny in a big haystack, for example, those are places where we need enhanced perception. If we look from far away at this bone CT scan, this is what I get. But this is what I really wish to have. And what is the picture on our right? It's called ambient light occlusion. I have changed the shading in my model such that things that are hidden directly from the light are darker, and it really enhances the perception of this model in 3 dimensions. So just to summarize, here's the old way to do graphics, and here's the new way, doing ambient light, occlusion, and shadows. So using ray tracing and path tracing are going to be the way to do this type of rendering. But we're going to look at the requirements for this application to run. Let's review. I don't want to offend anyone here. If you've taken Computer Graphics 101, you know all this, but we're going to review our classics, okay? Now, in the past, the conventional OpenGL rendering was to project polygonal models from a 3D world to a 2D screen. Doing this projection, we lose the sense of where are the lights, what is the illumination on my model, and we lose that ability to do enhanced visualization. With ray tracing, we do the opposite. I've taken this slide here from Pete Shirley at NVIDIA. This is it explains very quickly, in a very synthetic way, excuse me here a second, the way ray tracing works. We go from the eye through the pixel into the 3D world, and at that point in time, we are able to see our lights and to see all the interactions around us. So at the beginning, we used to do what we call ambient lighting, so really dull lighting. Then we added diffuse lighting, where, as you can see here, surfaces which point in a different direction, they have a different illumination. This was getting better, but it's still the old way of doing OpenGL rendering. Then we added shadows, and right away something a little bit better came up. But those shadows are they're called hard shadows in our world. What we want is soft shadows, because we have to account for the fact that light sources are not point sources, but they are diffuse sources. So all of this is done via ray tracing. We have ambient, diffuse lighting, and soft shadows. Now, as you know, often the makeup will fix it. It's enough to change the properties of the material to make it reflective. And at this point, we have ambient, diffuse, soft shadows, and reflection. And we're almost there to the full requirements, but we also need depth of field. Okay, look at those three images. Well, if I want to focus on this particular teapot here, it's easy enough to blur out what's in front, what's in the back, and then we have a really nice display here available for us. How do I do this? I have two solutions, fortunately. NVIDIA, with the RTX technology, delivers now interactive ray tracing, and this is really good because it follows. This is driven by the movie industry, which is always hungry for more cycle and more photorealistic rendering, and the efforts that NVIDIA put in the last 10 years have been realized now through the NVIDIA RTX technology, which enables interactive ray tracing. Well, the competitors are not just sitting back and doing nothing. Intel has an equivalent solution. Actually, here at the ParaView Supercomputing Center this morning, I was teaching the lecture on ray tracing, and we were able to demonstrate that those ray tracing features using the Intel Osprey library, which is also an open source development based on the ISPC technology, which enables full multi-threaded support on the Intel chips. Now, ParaView, that's the software part, that's the application part, is our benchmarking platform. It enables both the use of the Osprey ray tracing library running on the CPU with full multi-threaded support, or using the NVIDIA Viz RTX library using the GPU for even faster rendering. So I've got pointers for you if you want more information when you'll get a copy of my presentation here. Well, before getting to the surprise, I'll just be bold and I will switch to this particular point here and show you what it does, how does it work in real time. So this demonstration here, okay, I made a first mistake. This laptop I have here is equipped with the NVIDIA RTX technology. So the picture here I have on my slide actually can be done interactively, and as you see here, I'm able to move through my scene in an interactive fashion this is pretty chaotic motion, but I have the full ray tracing support. Okay, I won't take any more risks with this. Now, surprise, I said. Well, I was looking at the course notes from SIGGRAPH 2019 this year, and there was a tutorial by NVIDIA, are we done with ray tracing? And I said, oh my gosh, I'm going to talk about ray tracing, and those folks are saying it's a solved problem. No, no, no. We'll see more during my talk. This is not by far a solved problem. So let's look at the first showcase. Our first showcase is about volume rendering with ray tracing, and it's really raycasting because we launch rays through the volume, and we accumulate a certain color and opacity through a volume of a scalar field using what we call raycasting. Now, raycasting and volume rendering can be done in two different ways. One of them is with texture-based technique, slicing our volume of data with multiple slices which are accumulated and composed, or else with raycasting, again, going for each pixel in my screen, going into the model and looking at the data. And you'll see the video, you'll understand immediately the idea. Now, our showcase dealt with a simulation of a grid with 10 billion data points. And in that case, I'm actually looking at all of them in parallel. This is the grid size. We ran this simulation on pitch date at CSCS. And we did the visualization also on pitch date using ParaView and using the NVIDIA library. A paper was just published a few weeks ago now about this evaluation I've done, so you're also welcome to look at more details in that publication if you wish. Now, we have a volume of temperature data, so this is a fluid animation with the mixing of a cold and a hot fluid, and as you can tell from this little icon here, we can separate the different fluids, the different temperature field with different colors and different opacities. And the idea is that we can mix different volumes of different intensities, as you can see here, the hot and the cold fluids together. And really, here I have a cryptic illustration of the process. At regular spacing through the volume, I will sample my grid and get the intensity and colors of my ray traced sample. So this is really the idea. But as you will see, as I go, as I zoom into the volume, if I don't sample the data in a fashion, at high resolution, I want to say, then I will get artifacts. So I really have to sample at the right resolution when I zoom into my volume. 3 alternatives were tested, actually. So I repeat, the idea was, first of all, on our NVIDIA Pascal GPUs, using the NVIDIA Index plugin, or using the native implementation of ParaView, which is a ray-traced mapper implemented on the GPU, or else the method using Intel Osprey with full multi-threaded support on our 36-core nodes. So using TBB is actually the key to get all the multi-threading we need for our application. Is the comparison fair? Is that fair to compare a CPU and a GPU? Well, it turns out, yes, it is fair, absolutely. I have here a link for you to test, to look at this SIGGRAPH from last year, where you see a benchmark that was done by somebody else. So I don't have any bias towards the benchmark, and they also showed that similar performance was attained with both libraries. So I will now show you the movie so that we know this is about visualization, right? So there's the movie. So this is a collaboration with my colleague Alexander Blas from the University of Twente in in Netherlands. So there is the simulation here. Okay, we have a hot plate and a cold plate separating a volume of liquid. One of them is heated from the bottom, and we're looking at a temperature field. In 3D, as we move through the volume, now this is not real-time visualization, okay? This is a movie. You have to remember that in visualization, the first hurdle is to get the 10 gigabytes of data into the GPU. And that's not instantaneous, all right? So this movie is calculated via a batch job. And for every frame in the simulation, I'm able to do this ray tracing through the volume. So here we see very well those different waves going through the volume of data. And we're going to, in the simulation we've done, we've actually run, as you can see, different cases where in changing different parameters of the simulations, we were able to get different flow regime visualized. I'm going to run through just a few more seconds of this video to show you how, as we move in closer to the plates, we can get some really fine details about the behavior of this fluid and about the turbulence that is triggered by the physical phenomena. All right, so performance of this is interactive for the setup of the visualization, in the sense that using a parallel system, a parallel set of compute nodes, I was able to load the 10 billion points, which is actually 40 gigabytes of data, because the data is floating point number, and I can set up all my visualization through this interactive application. All right, so enough for this video. I'll return to my presentation. Implementation details. What are the limitations here? Well, the GPU's memory is actually the limitation. I cannot, on the Pascal GPUs I have on PITS date, I cannot load 40 gigabytes of data. I'm limited to 16 gigabytes. So I must go parallel, actually. On the compute nodes with Intel Broadwell CPUs, here the CPU's memory is the limit, but most CPUs now are the so-called fat memory nodes. At CSCS, we only have 128 gigabytes, but I know many systems around the world have even bigger size memory attached to their node. So in that case, a grid of size 3,000 cube can fit on a single node. I have a couple of slides here about performance. This is for your documentation later on. I don't want to spend so much time talking about it. But one key message of this first slide is that using the CPU-only solution here, the startup time is just about 1.3 seconds for 10 gig. No, I apologize, for 2.2 gigabytes of data, far less than using the GPU. Because here, using the GPU, we have to pay the cost of loading data from disk to the CPU, and then from the CPU to the GPU. So there's really a trade-off that I have to find when looking at big data, especially in the case of a movie where I load the data once, I do one image, and then I throw everything away, and I go to my next time step. Finally, for the full-size grid running in parallel, so this is my size, I was getting, almost 2 frames per second. This is enough for interactive debugging of my visualization, and then in batch mode, I run my movie. So that was my first showcase. Second showcase is from ray tracing to path tracing. Let's go back to the previous example here. Well, yeah, it's pretty good, but not enough. this, I want water inside the cylinder here, so I need refraction, okay? This allows me to do semi-transparent medium. And in fact, the cylinder is not filled with water. We will explain that later on. And there's nothing new, you would say, about this visualization. We've done, and look at go to the NVIDIA booth at SIGGRAPH or at Supercomputing. They have far fancier computer graphics. So nothing new here. What is new is that we can do this interactively today. This morning, when I was teaching at the ParaView Center, I had exactly that demonstrations running live. So, as I said, well, it's not really that the cylinder is filled with water. It's only the interface that matters. You remember Physics 101, Snell's law, optics? The light diffraction, that's what we are implementing now to do our ray tracing. So I can now have a nice teapot in glass. I have here two pictures. One of them is kind of noisy. One of them is the fully converged image. This is the so-called progressive rendering, and this is why the application is interactive. I can do incremental rendering of my image all the way to full quality. Let's look how I can apply this. So I can do semi-transparent materials. I can do diffraction. Let's look how I can apply this to my second showcase, which is air entrainment in a plunging jet. This is a simulation for my colleagues at ETH Zurich in the computational science department, led by Professor Petros Koumoutsakos. We have a jet of water, and this is the old way of doing our graphics. We used to focus on the air bubbles. So the air bubbles inside the liquid here are basically an isosurface of volume fraction, 0.5. That's the old way of doing graphics, where we focus on the air bubbles. But we shouldn't focus on the bubbles, really. It's only air after all, right? So we go back to the water instead. We go to the water-air interface, and then we're able to visualize this, to see through the block of water. Here's a clear snapshot of the beginning of this simulation. And then we have all the other special effects you would want. So for example, here you see some really nice reflection of the grid lines on the surface of the water, and then you have diffraction and all those other things. So I will show you the movie in a couple of minutes, and you'll be able to appreciate how this new ray tracing technology helps in getting really highly realistic volumes. Here's another snapshot I have taken. So here's the surface of the water, if you want and then we are inside the liquid, immersed into the liquid, and we're looking at those bubbles coming up and moving around. I have, in the presentation you will receive in my PDF file, you have a link to a site at CSCS where you can download those movies and you can play those movies again for your pleasure and to share with your colleagues. I'm going to show you here my local copy of the movie to make it faster, so I don't have to go through internet. So this is the movie here. So we start with a still block of water, and then this jet of water is now entering at pretty high speed into the column of water, and we have all kinds of phenomena taking place. I talked about interactive ray tracing. Yes, it's interactive. Remember that thanks to the progressive rendering feature of the ParaView application, which enables incremental incremental renderings, I'm able to benchmark all this visualization at interactive speed. And then as far as the rendering of the movie, I've actually done a very high resolution rendering using 400 samples per pixel, okay? And using, which are the GPUs which are on Pitt's Day now, which are in fact rather old, they're Pascal generation. I am able to do this type of rendering in, if I record, about 20 seconds per image. All right, this is for the final high quality rendering. So we've got all kinds of simulation features that we highlight in this particular movie. But really, the scientists have reported that the use of ray tracing has really changed the way they looked at their simulation data. Because for the first time, we also, instead of using lower quality, lower resolution data simulation, we are able to go to very high resolution data grids. So in that particular case, the grid was several, if I recall, just a couple of giga points per time step. Very good. So I'll just point out to this particular word here, Viz RTX. This is the library provided by NVIDIA which implements ray tracing and which takes advantage of the RTX core on the new generation of GPUs. Well, are we done with ray tracing? Back to my original question. Well, in Raytracing James chapter 11, I found exactly what I needed to illustrate the problem. No, in fact, we're not done with ray tracing. I had all kinds of trouble to fine-tune my visualization of the water, and perhaps you didn't notice, but there was no container around my volume of water. You can watch back the video at your desk next week, and you'll see there's no container. Why so? It's very difficult to do on the computer, because the computer uses floating point precision. Remember, this is the story of all simulation data. We have to deal with the limits of floating point precision. So in a fish tank, forget the fish, but the water here, what's the boundary between the walls and the liquid? There should be no physical boundary, or should there be a little gap, or should the boundary here overlap? Those are not rhetorical questions. They are really very important. Should we implement unique borders, an additional air gap? Because that epsilon is what kills me to do an accurate rendering with ray tracing, because when I trace rays through the volume of water, it finds that epsilon empty gap between the glass and the water, and then, may I say, it just freaks out. So the movie you saw was very finely tuned, but we don't have a general solution yet, and that's why I call this work in progress. My hardware, just for details, I have the lowest RTX GPU I could find, actually. It's only an RTX 2060 with 1920 CUDA cores. What is important is to have a very recent NVIDIA driver which supports Optix 6. Optix is yet another library from NVIDIA, a lower level library on top of which Viz RTX is implemented. And then my visualization cluster, the CSCS Cray supercomputer, I have those Pascal GPUs. They are pre-RTX generation, but still, thanks to an updated driver, I can run that not at full speed perhaps, but I can run that at a very decent level of performance. I'll get to my conclusion. Interactive ray-based scientific visualization really is now changing our world. The fact that it's interactive, because most important in visualization is to look for an interesting feature. Okay, a priori we don't know what an interesting visualization will be. We have some new data. We need to work with the scientists in finding the interesting features. Doing this interactively is far easier, as you would imagine, especially with big data. So enhanced perception, additional tricks of computer graphics is what I need to do this job. We've gone through 2 different showcases. One of them is volume rendering, traversing a volume with rays which sample the data at a different resolution. And we've gone through a second showcase, which was ray tracing and path tracing, using advanced lighting effects such as refraction, etc., to give more realism to the visualization. Both of those methods, actually, volume rendering, this is the subject of my paper in the Journal of Parallel Computing, and then the ray tracing and path tracing, both of those are implemented today in the ParaView application with hybrid parallelism, such that I can mix MPI, CUDA, TBB on the node, and really exploit all the parallelism available on the hardware to achieve my visualization. So several billion vertices now. I hope it's going to become routine when applied when applying those ray tracing applications. And with this, I will thank you all for the attention. Thank you. I'm open to questions.